So for Monday's pre-lecture video, I wanted to go over principles of conductors in electrostatic equilibrium. Remember that when we started chapter 22, I mentioned that you should really pay close attention to the language they use, because when we first start talking about Gauss's law and using it to find electric fields, the charge distributions that we're looking at are insulators. But at the end of the chapter, we look at conductors. And I chose to do this because I was worried that we might not have as much time as I would like in class. So at least we'll get to see it first before we go through it in class. So basically what we're talking about at the end of the chapter is conductors that are in what we call electrostatic equilibrium. Now, electrostatic means that the charges are at rest, and equilibrium means that there's no reason for them to move again, that they should be staying at rest. So basically, we observe 4 different things that are true in this situation when the conductors are in electrostatic equilibrium. First of all, we find that all the charge that the conductor would have would be on the surface of the conductor. Second, we would find that the electric field inside the conductor would be equal to 0. Third, we would find that the electric field is perpendicular to the surface of the conductor. That would be outside of the conductor. And the magnitude of its strength, oh, this didn't come out right in here, is sigma over epsilon naught. So we're going to go through and see why these 4 things are true. First of all, why would the charge be on the surface? Well, let's suppose I have a conductor and it has some sort of net charge, and we let it be throughout the conductor. Now I know that I put positive charges and it'll really be the electrons that move, but just humor me. So because these charges are like charges, as I've drawn them on the conductor, and they're in close proximity to each other, they're going to exert a repulsive force on each other. And this will cause the charge to redistribute. And basically what will happen is the excess charge will move as far away as it can. The charges will move as far away from each other as they can. And basically the furthest they can go is to the surface of the conductor and then sort of spread themselves out evenly. And so this is sort of the transition of where they'll go to when they're in equilibrium. Any charge that would be inside the conductor would upset the equilibrium until it moved to the farthest area of the conductor, which would be the surface. So that's why number 1 is true. Number 2 says the electric field within the conductor is 0. Well, here we have our conductor, all the charges on the surface. And let's say that we wanted to find the electric field inside of the surface. We're going to use Gauss's law, and here is our Gaussian surface, is the purple line right here. And so remember, the Gauss's law says that the total electric flux through the closed area is equal to the charge enclosed over epsilon naught. Well, the charge enclosed, because all the charge is in the surface, is 0. And the only way that we can satisfy this equation then of the integral of E dot dA is that the E must be 0, because the area is not equal to 0. So the electric field, so we conclude then that the electric field is 0 inside the conductor. It should make sense to you because when we're inside the conductor, there's no charge that is creating an electric field. The next thing that we find to be true is the electric field is perpendicular to the surface. So what we're going to do is we're going to draw a little piece of the surface of the conductor, and we will sort of prove that the electric field has to be perpendicular by entertaining the idea that what if it isn't? What if the electric field is at an angle to the surface, which means then there's a component of the electric field which is parallel to the surface and a component of the field which is perpendicular. However, when these charges look and see that parallel electric field, they would feel a force from the parallel electric field, and that would make them want to move along the surface. They would have to move parallel or anti-parallel to the electric field. However, they're in equilibrium. So the charges aren't moving. Therefore, the electric field can only have a perpendicular component. And finally, the last conclusion is that the electric field at the surface is equal to sigma over epsilon naught. Sigma is a way that we express charge density. It's charge per unit area. So we're going to use Gauss's law to show that this is true. That's how we find the electric field. And the shape of the surface that we're going to use is going to be a cylinder. And notice we have the electric field at the surface. It's perpendicular to the surface everywhere. And inside the conductor, the electric field is 0. So if we look at the cylinder has the sides, it has the bottom, and it has the top. At the sides, for the most part, the electric field is perpendicular to dA, so the flux from the sides is 0. At the bottom, the electric field is equal to 0, so again, there's no contribution to the flux. And so we only have the electric field at the top, which is equal to the charge that we enclosed over epsilon naught. So let's go to the next slide. So we have E dot dA at the top. The electric field and the area vector are parallel to each other, so that turns into E dA, and that's equal to the charge enclosed over epsilon naught. The electric field comes out, and we have the integral of dA is the charge enclosed over epsilon naught. It's E times A equals the charge enclosed over epsilon naught. Electric field, we saw for that, and Q over A is going to be sigma over epsilon naught. And voila! The electric field is given by sigma over epsilon naught at the surface of a conductor. Now, one interesting thing to consider is what if we have a conductor, but it has a cavity inside of it? So I'm just kind of coloring it so we can tell the difference between the conductor and the cavity. And then what if I put a charge inside of this, and that charge is a positive Q? All right, well, if we think about it, that charge is going to create an electric field. But what will happen is when the charges in the conductor see that electric field, what happens is the electrons will feel a force inward in the opposite direction, and protons will feel a force in the opposite direction. So what will happen I'm going to just draw my cavity bigger so I have more room. Here's my Q, it's positive. And what has happened is negative charge has gathered on this inside surface of the cavity, leaving positive charge on the outside. Now, we know that like somewhere around here, if we took a Gaussian surface, it would tell us that the electric field was equal to 0 because we're inside a conductor, which means the Q enclosed has to be equal to 0. And that means that plus Q, and if we add to that the negative charge on the inner surface, has to be equal to 0 for that to be true. So then that tells us that this charge on the surface is equal to minus Q. So it's kind of interesting when you think about it. And so that's what would happen to the conductor. And so we'll look at some applications of that both in the homework and hopefully in class. Hopefully this will help clear up. The fact that we've covered it in this pre-lecture video will make it a little bit easier for us when we look at it in class.